think it should be recording now.
All right, so Jiahua, we're all clear. Sure, okay.
Should be, or maybe
I'll try my best.
Or maybe I unplug it, but you check that the battery.
Yeah.
Yeah, I do that.
Okay, yeah, maybe it's better. I just don't want to break your computer.
So let me put yours in focus. You're in focus.
Okay, I will start. Okay. So this will be a very elementary talk, but maybe interesting for you, not? So we want to start with wave equation for the Coulomb potential. So like actually not see. I will pursue on its own for the moment. We have over h squared from constant, and we solve this eigenvalue problem. The wave equation, stationary Schrodinger equation. The only assumption I made is that the potential is extreme invariant. This automatically will write that if we define the
assumption you make is is what the potential is
rotational invariant.
rotation invariant.
Yes. So if we make the angular momentum operator by the usual way, so the place cross with the momentum, it's going to be commutated with the Hamilton operator, which is a generalization of the fact that the constant, if you have rotational invariant potential, the angular momentum is constant.
So UR is more general than whole potential right now?
Yeah, right now, yes.
Yeah.
And we know that this square is just nothing but a spherical Laplacian negative. So this sort of suggested that we are going to use the spherical coordinates. We are going to use that. But before that, even before that, I will make assumption for now that it's Coulomb potential. And if we do this, there's another way to reduce the question, which is less known, so very interesting. It's called parabolic coordinates. So which is x square root of c theta, so sine of t, y is square root of c theta, sine of t, and the z is just 1/2 minus theta. So what's the meaning of this thing? It's just, okay, we have these z axes, so we make those families of rotational invariant paraboloid parameterized by the c and theta. Then we make those family and use another angle phi to make some new coordinates. My claim is that on the coordinate system, we can also reduce this question and solve it explicitly. Question for those coordinates now?
I think you should talk a little louder. Because I'm having a hard time to understand, and I'm sure they're not gonna.
Sure, yeah, I'll try my best. So this is coordinate, yes.
Good. Oh, and just so what is it? So you have x squared plus y squared is c times theta. And then c squared is c minus theta.
I think like this is for example 1/2 c minus x squared plus y squared over c, and this will be 1/2 negative theta plus c, sorry, x squared plus y squared over theta. Probably I should extend it. So it's the correct orientation of paraboloid. So, and the angle phi is the usual. So this is especially useful for scattering. scattering. So because if we have a wave, usually there's a direction, for example, along this axis, then because these coordinates are especially for this axis, so in the scattering, people always use this, or very often use this for Coulomb potential. For example, you can derive the result. Formula from these coordinates, because this equation will be reduced to this two system. C F1 over C plus 1/2 beta C minus M squared over 4C beta 1 alpha F1. And same thing for F2 and beta 2, and all for it. Where we write C equals F1, F2, C to eta, e to the power pi and C. If you put this separation of variable plug in here, the original Schrodinger equation, it will reduce to these two and in the same form basically, and they can be solved explicitly by the similar form of the spherical coordinates. But because we choose this direction particularly, so this will be useful, for example, to the started scattering. This is just briefly introduction of the parabolic coordinates, and now we'll move to spherical coordinates.
So this way you reduce it to two 1D equations that
so I should let you know beta 1 plus beta 2 just is the separation constant. They are called parabolic quantum numbers.
So you're interested in plane waves, or like the fact that plane wave scattering? Is that the idea?
Yeah, that's a particular design, or it's very useful to study the plane wave scattering if we are in this direction.
Okay.
because then the level sets will be on those kind of parabolas.
I don't think so, but it will be related.
Mm.
Yeah, the function will be the combination. So we can solve the Schrodinger equation by these separation variables in these coordinates. And people always use them for the parabolic, sorry, for the scattering. Yes.
And I'm still lost. How to see it.
These are the new coordinates, because the eta and phi are the new coordinates. X, Y, Z are the original coordinates. You do this change of variable.
How are you change that?
So under this cos eta and phi, the Laplacian will have a form by cos eta.
I mean, like if you're given X, Y,
Mhm.
how can you determine C?
You just solve this in
Oh, so the last set is like
yeah 1/2 cos minus theta.
oh.
And the potential is so
Potential is alpha over.
yeah, but and there it's E times C
Yes.
minus M squared over 4C
Yes.
plus a constant.
Plus yeah v1 constant.
And alpha is that.
How can we determine if I want to?
It's not determined. It's determined by these wave equations. Basically, if see what condition you want to put. For example, if you want to put, I think if you want L2 on the whole axis, there are some conditions for beta 1 and beta 2. For example, if you want to solve the real heterogeneity, you are ask to on the whole axis. And this beta 1 and beta 2, I think is 1 over some integer from that from the equation. But if you want to solve the wave, say
That's all. Any choice of beta 1 plus beta 2 equal 1 will give you a solution to the PDE.
Right.
And then it's may or may not be into
yes.
If the vendors have to be positive, or just not?
I think in this formula we don't need it to be positive, but I think when we solve the PDE, it will be positive. And you solve the ODE. But actually, I don't think it matters because alpha could be negative or positive. Yeah, so for it.
And so you can recover all the bound states this way as well?
Yeah, exactly. Yes,
Even with the spherical harmonics?
right, without spherical. If you look at non-efficiency look, this section is just after the spherical coordinate section. So this. Another question, then go to the spherical. There you go.
And well, so is this equation easy to solve? Can you get explicit solutions?
Yes, it will be very similar to the spherical in the case of spherical. It will also be solved by some special functions. Yeah. Actually, the same special functions, same form. Okay. So now let me read this. So I will now use spherical coordinates. Oh, this I don't need to write the formula for spherical coordinates. Everyone knows what it is. And in this time, we do these separation variables. The usual way. So these are the eigenfunctions. Of the Laplacian on the sphere, the spherical harmonics.
Okay, so can I ask you to at least draw the spherical coordinates because the exact meaning of theta and phi depends on the.
It doesn't matter for us, but I always use this convention.
Okay, so the opposite of.
Yeah, but when I was teaching calculus, I should use the other way.
Those are physicists.
Yeah, I'm sorry.
This is what they do also in calculus.
In calculus, they changed it. I'm sorry. So they have numbers, they have names in this case, right? So L is a single, so quantum number, and A is the magnetic quantum number. Even in this level, without solving the equation, we know that M could be from I don't know, it could be 0, 1. Yeah, well, minus minus. Is it?
That's between minus and.
Yeah, yeah, you're right. Sorry.
I think you have 2 plus 1.
So we have these 2 other +1 states with the same, well, they will have same eigenvalue with its states. So this is general degeneration for adverse rotational invariant potential. But for Coulomb, in the case of Coulomb, there will be an extra degeneration. If I have time, I will explain that. Okay, so now suppose we plug in this separation variable. For R, then we will reduce to R1 plus over R Point minus L plus 1 plus third plus 2m over h squared E minus UR times R over here. So now I will make the assumption for the potential. I will in particular do Coulomb potential now. I will assume alpha is positive for now, but all the formula will equally holds when alpha is negative. I will tell you later. For now, I just say the potential is repulsive. And I will make the assumption that I will choose the units. With mass by n length by h squared over an alpha and the prime by h cubed over an alpha squared. So this is called Coulomb units. They are really units used by people. And that's my excuse that under this units, the equation will be R double prime plus Q over R prime plus Q E minus 1 over R minus L plus 1 over R squared times R. The difference from the notes we used before is that there are two potential. So if you don't want these two, we can always do the scaling by some other way. But because these some units people really use, so I will solve this equation instead of this equation. So there will be a two.
And there is a minus 1 over R.
Yes.
So now shouldn't there at least be a sign?
Yeah, the sign is fixed by this function.
Sure. And so otherwise it would be the same except for the sign here.
Yeah, I think the otherwise it will be plus if I change the coordinates. In this equation we are interested.
And sorry, so R is in factor of
Yeah, I want this times R.
yeah, but so the 2 is only in factor of the C.
In fact of C
Same
C is
comparison.
like,
Yes, what we had.
bracket.
so it is so 2 E 2 over R
Yes.
2L plus 1.
Yes,
And there is no C.
yes.
You said that you take alpha too, or did I something?
I use this units.
Oh,
So
oh, okay,
alpha
okay.
m and the Planck
Alright.
constant will be applied.
Alright.
So now I will solve this equation. So because this is a repulsive case, so all the states will have positive energy.
And where did the time? Does it matter? Because E is related to the time.
Yeah, but these units will give you a time dimension. If you calculate the
Yeah, but where does so you're the equation that is instantaneous?
yeah, but I think that Planck
But it's
constant has some time dimension inside it. So it's energy or something.
But the equation doesn't have time, so.
Yeah.
If we scale time on that, it doesn't change.
That's right, but I think unless we do that scaling, if we only have the first two, these three number is not determined. because we have three constants. So we have three freedom to scale everything. And what I want to say is that if we scale time in the correct way, all these three constants will be one. I don't think so.
It's like the world, like the side that depends on time. It's like that side times the phase.
Oh, I think the time relates here because this. Yeah, but this is from
But I
the.
think so E, because your thing would oscillate like e to the I e t. And so I imagine this is the thing that
Yeah,
should be scaled.
Exactly. Yes. Okay. So again, this is the repulsive potential, so the energy should be positive. We should solve the traits. So I will write Q equals K squared, and I will always make the convention that K is positive. It doesn't matter actually too much if we want to choose K equals negative, but why not K positive? And under this assumption, we can solve it. So for now, I still put at here, not 0. We solve that by the assumption that R, when R goes to 0, the function should bound it. Actually, not only bounded for this. Sorry. Yeah, bounded. That's a physical solution, and the solution can be written by RKL equals some constant, which is important for us to plus 1 factorial UKR to the power n e to the power IKR times this function I will take as L plus 1 to L plus 2 negative 2 IKR. Well, this is the confluent geometric function, hypergeometric function, which is on the notes and the definition, which is entire on the whole domain, on the whole complex plane. And the thing, the first term is 1, I think. So this thing really has this property.
So it's CKL divided by
2L plus 1 factorial.
This whole thing is bounded.
The thing will actually,
As R is large for R.
when R is large, it's a very good question. We were very interested in that case actually. But when L equals 0, you are right, it's bound. The result is it's bound.
But you said analytic, no?
Say it again?
Didn't you say it's analytic function in the complex plane?
It's entire function. Analytic on the whole.
So if it's bounded, that it should be constant.
But you only take R to be real.
Yeah, exactly. That's the point.
Oh,
Yeah. Thank you. Actually, that's a very good question. We are very interested in this. But before we go to this constant and the asymptotic behavior, I will first give you idea why we have this factor. And this is related to our question later. I haven't read this equation. So what we expect when R is small and big. So when R goes to 0, let's look at the equation. Which is dominant term, or which terms could be ignored. So we have something over R squared here, which dominates these two other terms. So we should ignore these two other terms. The equation will become so star will become, so do some with here. R square times R double prime minus L plus 1 R equals 0. And we can solve it.
So there is a R times R.
Say it again. Oh, you mean this one?
Yeah.
I time so I time R.
I mean there is R 2R times R 5.
Yeah, but if you take double.
I see. I couldn't see the break.
Oh, sure. So we know that R is equal to this between. So if we want boundedness, this is the correct one. And this relates to the what Professor Schreiber told last time. When L equals 0, we have some constant and 1 over R, and if we multiply here, so it is let's say 0. It's R and the constant. This is not exactly true because there will be these things.
Sorry, say that again. So when R is equal to 0,
When L is equal to 0 and the times R here, because that's the equation we care, because that's the solution function we care. So this actually what Professor Schreiber called a limit circle. But there are two solutions we can put in the data. But when L is positive, this is the limit function. And that's why we have the term here, the first factor. May I read this? So let's study another.
Oh, I suppose it doesn't include the K.
Yeah, no.
It doesn't explain the K.
Yeah, it doesn't explain. So we let R goes to infinity. So what is dominant term? Okay. Those two terms will be dominated by the first term. And actually, we will ignore this term also. So these are very dangerous assumptions. Actually, we will see. So we will make this dangerous assumption and see what's the simple behavior.
Let's do that again.
So we will ignore this term, and this term. And this ignore this term actually is very dangerous. Actually, it's wrong. So but we will see explanation. Yeah. Because the Coulomb potential is not so weak for infinity, but at least it will have this behavior.
Why do you not enable terms?
When R is going to infinity, so we ignore it because there are 2 over R.
So we know that R is going to converge.
Yeah. These
are also allows for decay.
Yeah. Of course, this is very dangerous, but that does not make too much problem, I think, actually, compared to this term. This is more dangerous, I should say.
At least if you have something reasonably smooth, these are the terms that you could not ignore.
Exactly. And from this we solve the cost of it. So this explains this factor. So a clever way to solve this equation is actually we make this assumption. And solve W. Plug this to the equation and solve that. That's how to solve this equation much more easy compared to just plug that into automatic. But let's just keep this in mind. This is exactly wrong, and I'm always very interested in when this could happen. which potential will have this phenomenon. I think if UR is R to the negative n and n is bigger to 2, this could be correct, but I'm not very sure, and I don't know for the general.
At least I think it, well, the proof that we had last time, I think you could make it work, and we get something that would be the integral of U of R.
Yes.
Or an antiderivative of U of R, and if this is bounded, then you do it. So maybe even bigger than, strictly bigger than 1 would work.
I thought about n equals 2, but maybe right. I think when n equals 2, there are.
But then you have problems at 0.
Yeah, sure. Yeah, anyways, we'll see this is wrong later, and this relates to our question. But for now, we are good to solve it. So suppose we have this solution. And from now on, I was very focused on the constant here, which relates to the measure on the free transform figure. But there will be no difference between L equals 0 or positive. I will just assume L equals 0 from now. The general case is very similar, just more complicated to write. So just ignore that. So actually, will just be ck times e to the power of r with x over k plus 1, 2, and negative 2 pi kr. Okay. Now we have a first question. Is this obvious that the function is real or not? So I tell you this function is actually real. So that's why we will use that basis as a free transform meter. But I just want to ask, is this obvious or not? Not for me. So this is the real, and I have explanation here. So we will use this formula. Equals gamma function over 2 pi I, the integral for t minus z to the power negative r, t times t to the power of minus gamma dt. So how do we get that? This is from the Laplace method for ODE. I don't think I have time to study this, but basically for any linear ODE, even autonomous, I think ODE, you can solve that by this Laplace. Sorry, the coefficient will have some polynomial, but you can solve it by Laplace method, which is basically some Laplace transform, and you can solve the ODE by the complex this integral, and the C is this. So suppose this is t equals 0, and this is t equals that. The loop is this. So how does this equal? We will make this change the variable from it group.
I don't understand what is t equals z. What is t?
T is the integral.
Okay, and where is t equals 0?
So t equals 0 is the point here. This is a complex penalty. And we will make a loop around these two groups.
Around 0 and z.
Yes. So basically, this because we define the logarithm or argument in this image. So this is the segment for the It's close to infinity, so it's closed. Yeah. Actually, you can make use of any closed loop as long as some condition is satisfied. That's the method of Laplace. So let's make this change a variable. T equals 2I pair. Sorry. Let me first write down what is R K now. It's CK into the power of K over 2pi. And we is include into the power T over 1 plus 2I pair over T to the power 1 over K minus 1 into the power negative 2 T. So now this is negative value. Sorry. Right. Okay. Then we'll make this change of variable. T equals 2I r. This minus 1 half. Then this will be negative CK over 4I r. Under another loop, into the power 2I r. This plus 1 half. Over 2 minus 1 times this minus 1 half over 2 minus 1. Yes. And what's a loop? So this, yes. CK is a constant you always keep.
EIKR is the
Yeah.
and then minus alpha is minus I over K minus 1.
Yes.
And then you replace the Z. And then alpha minus gamma. It's I over K.
Yes.
Minus 1.
Yeah, but we have T fitted here. So it's not T minus that. It's and when we make this change of variable, it will be in this way. And I will just tell you what is C prime because this change of variable is like a rotation by 90 degrees or something in the scale. So on the S plane, we grab this. So this is negative 1 half, this is 1 half. Okay. Now let me ask, is this obvious or not? It's real or not? So if you look at the number of sheets, they stopped here and they tell you it's obvious. And I spend a bit of time why it's real, but it's actually true because if we carefully compare the point here and here, you will see that they are conjugate to each other. And this ds, well, this is plotted by this, because they are in different direction. So this is very real.
So did they call this obvious, or did they call the hypergeometric function obvious?
They think this is obvious to be good.
Okay,
Not bad.
that's a little bit reasonable.
Right.
Of course, yeah, that hypergeometric function is real. It's real. Yeah, of course.
Okay.
So just what you need. So if you have S and something like, and you change the real part of S, then the contribution.
So the easier way is if you just look at let me change this loop a little bit. It's easier to see. And suppose we are on negative 1 half and 1 half, and we plug in this is one hard part. I don't know which channel it's about, I think. This is making 1/2 plus antenna. You plug in here,
So then you
they
have-
are the contribute. But there will be more obvious way to see that in a moment. So I hope you believe now, but even if you believe me, why? Okay, now we have this loop. And we basically know that the left part and the right part is congregate to each other. So why don't we break them to two groups? So that's why they define function g. And make use of these terms. So in the notes I give you, there will be a function g, I defined by the expansion, but I'm cheating there because this is not a Laurent expansion or type expansion. It converges nowhere. It's an expansion. This is just a symptotic expansion. So not absolute value is not going to the terms, but only relative to the quotient values. So that's a cheating way to define G, but it's an easy way to define G. So the real way to define G is the following. If we define to be gamma function over to I, one plus t over z, the power negative alpha, t to the power beta minus 1, to the power t dt. So I have just erased the integral for f, but if you look at carefully, I should erase this moment. I think C1 is of this group. Let me do this. And you can see that we just do the input twice. So this is the definition for G. They just equal for this one, and they break that to two parts. And that's corresponding to the fact that we do this transformation to be contrary to each other. So what we will do now, we will express this solution by G. Okay. By use of the formula.
And so C1 is the smaller contour that goes around Z, but
Yeah.
not around Z.
Yes. That's because we just break these two loops, which will correspond to 0.
And each of them contributes.
Yeah. Each of them will contribute to the integral of f by these two. Yeah. But one of them is given by G, another one of them will be given by G in another way. So that gives us formula.
But each of them will contribute to the real parts.
If we do the change of variable, they will conjugate to each other.
Each of the curve is conjugated. They are conjugated to each other.
Yeah. So if we break the integral of f to these two loops, so we'll have this formula. That alpha gamma z equals the ratio of gamma function negative z to negative alpha, 3 alpha plus gamma plus 1 negative z plus ratio of gamma function e to the power of t alpha minus gamma and g gamma minus alpha or minus alpha. Look at this formula for a moment. I'm cheating again here. And this is actually very subtle. This is very subtle problem. You remember I defined G by this asymptotic expansion. So this actually gives the asymptotic expansion for S. But we have a question for the expansion, asymptotic expansion always. That you see there we have negative one here. Suppose we have a real positive value set. What is negative one? We define the branch transpose this line. Right? But how about negative one? And the same problem happens when 0 is a negative number. We will have trouble here. For our use, for our original question, we will see that this is pure imaginary. So actually down here, we will not have this trouble to understand. But this was a very confusing problem. So this is called Stokes problem. That in different axes, we will actually have different expansion formula. And actually what happens is that when this is positive, a positive number, actually when the real part, this is positive, the first term will be weak, much weaker compared to the second term. So in the expansion, we don't need the first term. And there's no trouble at all because the second term is well defined. Same way, if the real part of that is negative, then we will not have a second term in the expansion. The first term will actually much more strong compared to second. But we are in pure imaginary part, so even if you don't want to study this question, it's all right. But I just want to emphasize that we should be very careful with the expansion.
And the expansion, so you define G this way.
Yeah.
So where is the expansion?
If we define G in the other way, the series way.
So it's a series in Z.
Yes.
And so basically, if you try to expand around Z equals 0,
yes. But again, this is not Lohan expansion. This is asymptotic expansion.
Right.
There's no convergence.
Yeah,
I think Stokes is the first one who found this in the solved question by Coulomb. Instead of real numbers with complex numbers. But if we come back and sorry.
What did Stokes do?
Sorry?
What did Stokes, where did he find the problem?
He found that
if
it's a real number, then they have different asymptotic.
So was it like every in one direction?
Yeah, exactly. It's called Stokes. Okay, so let's plug in both these numbers. I will do this for you. But if we plug in pure imaginary number, then we will have something much better. So pk into the power over 2k over kr times the real part of exponential I negative ki derivative plus 1 over 3 logarithm of kr over gamma function times the G. So basically, if we plug in this thing, the two terms will just be conjugate to each other. Okay, and that's analytical explanation of the phenomenon we found. Just do the two loops, they're conjugate to each other. So from this expression, it's obvious that it's real. So the question about this, do you believe that's real? No. And they in the long repeats they said now it's obvious it's real. Okay, so this is the first remark or first problem we found for the solution, but just keep this thing in mind that Israel gives asymptotic behavior. We'll go to that. For now, let's go to the second question, is the CK question, which is the measure we're really interested. So what is the constant CK? So if this is additive function, we just normalize that. Right? But this is not additive function as explained last time. This could not be additive on the positive axis. So how do you do that? So now let's tentatively do this free transform. Just do the integration. Now this is real value, so we can do this, get a real number. Then, as we were told last time, we have the Pascal inequality. Sorry, equality. With some measure. I will normalize this by 2 pi as the usual Fourier transform. So this is a identity based on several identity we want to use. So I will normalize, or we would like to normalize that in a way that we choose CK such that this measure is identity 1. Okay, then we will have a Fourier transform method. This is, we can build it, but I just change the CK. Then we can kill this measure. Okay. So that's our goal.
Sorry. So you define the Fourier transform by taking f to say that it's f times r times rk.
Yes. Of this functional function. Yeah, by the notation of Professor Schlag last time, this is a phi. It's phi function. And if you lucky enough to check, this is like the
phi function is a function that can take 2 around 0.
Yes. This is bounded around 0. Actually, it's 0.
0. But then you see.
Yeah, we need a psi well function which is actually just this one without the part.
Without
the real part. But it's not so obvious, so I will explain further. But this is true that, or at least with the coefficient, just this is this part is the psi function or the well function.
But this is. Yeah. So the psi function is
the one that you are to go to positive.
Yeah. And this is, but which one is it? It's just a G or it's just the
one
inside the bracket?
Yeah, because otherwise it's not a solution.
Why you have times R?
Oh, I should say at the beginning that we need to so when we do the L2 integral in the space, in the 3 space, we will have this. So the integral of the space is like on the sphere and times r squared on the right radius. So if we do any L2 estimate, I guess we will have this on. And actually I should have. Oh, sorry. Thank you. Okay, so another way to say this is that as yes.
Yeah, okay. So this would be the same thing as normalizing the function if it was in L2.
Yes.
But because it's not in L2, you normalize it by 1/0.
Yeah, I'm going to write this that what we actually get is faster plus rk with prime integral r. This is that function if I'm whatever explanation you want to give this, but that's it.
So r squared times rk prime.
So of course this is just in discrete sense because we cannot take this is how they write this. So how you see that in the literature. And I haven't tell you how to find CK. Okay. So that's a big problem actually, a very difficult question generally, as we see last time. So if we believe that this is sort of the well function, we have the every part we want to find the picture already. So we have the well function, we have the p, and it's not hard to find theta. It's just the imagined part. This thing, and then you just plug in and coefficient.
Right at this stage, like so long as you have this, then you can just redefine by saying fk divided by the square root of 0 to k.
Well, we don't know what is 0 to k.
But then you, yes.
Yeah, we want to find 0 to k.
But at least we know like it exists, it's possible, but now we want to know what is the formula.
Right. I guess that's a question we care. Okay, so let's go back to that. Suppose again we have no potential, or the potential is so weak in the infinity. Then when r goes to infinity, I just told you that what it is, but didn't write it down. This time I keep this. Okay. You see, that's how we do things. What's the general solution for this ODE? It's just sine they are plus some constant. This is for phase shift. If we have potential, and for different number n, so different. Okay. Now, if we want to normalize that, what's the correct CK? So if you want to plug in the function last time, I don't know if I should do that, but you can try that. You will see that let's see the well function. CK, of course, will just be exponential like here, and the well function will just be I over 4. And what is 0 over k? It's just 2k over pi times the imaginary part of 1k. What is that? It's just so 1 over 2 pi. I normalized in the last time anyway, so actually in this case, that's fine. Of course, because this is just the, I would say this corresponds as an imaginary part or real part. So it will be
So
derived.
it's 2k over n times the imaginary part of n.
2k over pi. That's a formula from potential. But even without that formula, you will see this is the correct one, and ck equals 1 is the correct one. By just integrate this, it's not hard to see. We have this. So this is the correct asymptotic behavior if you want to normalize it. For the weak potential. Now we have this formula. We have asymptotic behavior of G. We have expansion there. We just take the first term, which is 1. So we ignore this G and calculate the real part of this thing. Right.
Can you say that again?
So the asymptotic behavior of G we know is defined by the series. So the first term is 1, the other goes to 0. So we saw it, yeah. And we have this part, real part of this thing. Okay. But it will not be this. But when R goes infinity, this will be ck at the same constant 1 over the gamma function, but we take out the value times QR sine KR minus 1 over K, logarithm of 2KR plus the phase drift. This is just the argument of gamma function. Okay. And you see again that in the real solution, the asymptotic behavior is not the one I raised. We have this extra term. That's because the Coulomb potential is not so weak. So we must have this. Okay, and you will see that this makes perfect sense later. But for now, this is our result times ck. So you can guess what's the correct ck. It's the one that makes the things posing 1. Okay. So now we have a ck.
Wait, so question. So the asymptotics on the right,
Yes,
is you calculated from the thing that you just raised, right? You're not gluing this one with the one that was like there without the.
we can do that, but I don't do that here.
Okay.
For simple.
Okay, so you're kind of like ignoring the calculation without potential and
Yeah.
just keep going with this one.
Yeah. But this one is with potential because
Right, yeah. But this one is without the term like
Yeah.
prime.
yeah, if no potential this thing, so we guess this should be the correct one. And actually this is the correct one. So TK is which is 1 over the measure something. TK we call it gamma value. Okay, and we can calculate that by the gamma function behavior. So finally we will have 8 pi k over e to the power 2 pi k minus 1. Okay.
Sorry.
Yes.
Yes.
Yes, please.
Yeah, so this one you calculate the sort of like doing all like the variable integrals and so on, going to the geometric function, but
Yes.
Dropping the term that was like r prime
Yes.
over r.
Yes.
And now you did the other calculation where you dropped the potential and you saw that the term r prime over r was meaningful and it
Yes.
created your straight.
Yes.
How can you be sure that you're not making a mistake here?
Good point. I cannot do that until I use the recipe last time. But it's correct because actually, if you calculate Lansky, just take algo to take Lansky. If you see the notes for the slide, it is the same thing. Just go to infinity, calculate Lansky. Lansky and there is much more simple. And this is exactly what he get.
But wouldn't make more sense to, I mean, okay, I know that like everyone knows the answer, it's fine, but wouldn't it make more sense to put everything and then sort of try to analyze?
That's right. Yeah. But
I mean, of course, if you know the answer, it's a lot easier to prove
Yeah.
it, but
basic simplified proof, simplified version just scheme. The full proof is written in notes. If you read that, he just takes the limit floating into the last skin. The last skin there is dominated by this. The last skin is a constant dynamic. Actually, even this is done. That's why we can do this. So this is a very physical.
yeah, I guess.
Which is
Well,
correct.
if it works, it works.
Very, so then I miss it. So you take the, so you want to compute it using the Wronskian.
If we
Yeah.
want to do that by
So the Wronskian of three functions.
yeah, I guess you can do that if we
So it would be the Wronskian of RK and
so
With the growing.
yeah, last time I think in the notes professor started something like this.
oh,
Yeah, and which this behavior is like this, or exponential. And he calculated this by taking limit algorithm limit. Okay. And if we go care the asymptotic behavior of the measure, when k goes to 0, the CP score is just IK is perfectly. And CK will go to the integration here. The CK square is just the fourth frame. So this when k goes into we do have this. I don't know if I can speak more, but I want to give you explanation why we have this thing. Why we have this compared to the potential, that's not the case. So this has a purely classical explanation, actually. Suppose
and so just
yeah, please.
in your case, when k goes to infinity, you recover somehow what you could think of the L2 measure, k dk.
Yes.
So this is maybe not too surprising, but when k goes to 0, then you get something very tiny.
Yes, which is not the opposite case of the attractive Coulomb potential. If we do the attractive Coulomb potential, it will be 1 over square root of k. And if we normalize instead of by the momentum normalized by energy, it's constant. So there is something when k equals 0 in the attractive potential, which we also find.
So then those computations would become very different in the
For
case,
attractive.
in the attractive case.
So attractive is it's same. That's the previous definition. But you need to. This is very different. We don't have negative. Okay. So the solution is same. Just do this substitution. It's
Yeah.
same. But the CK, which I have it here, you can compare. CK is 2k e to the power significant over 2k times the gamma function. So minus 100, which is 7. Because these two things are different. And this gives you square root of 8 pi k over 1 minus e to the power 2 pi over 3. So different bottom and so different system. So we cannot just change r to negative r when we want to normalize that. But if you want to solve the equation, just change it. So now let me go to the explanation. Second. So in the classical picture, we are not in a wave, we are in we have a lot of particles shoot in this direction. So what will happen? Of course, we are being out. Is the picture the use of classical use of scattering?
So you'll send me a beam from below. And
Yeah, with the same direction. This the hyperbola. They are solved by Newton.
With the, so this would be a repulsive case.
Yeah, yeah. But actually, the result formula is same for the positive and negative. The distribution is same.
Yeah.
Okay. So what I want to say is that if we want a family of surface normal to this curve, it will not be the plane because of the potential, Coulomb potential of the hyperbola. The asymptotic surface normal to all of them is this. It's a curve or rotational curve given by this equation. So constant equals, so suppose this our z-axis and right here. The constant equals z plus 1 over k squared 1 k square root x squared plus y squared minus z. And we want to, if we want to study scattering by the quantum idea, in the quantum case, this is going to be the face or wavefront on the face. So the particle on this surface, they have same face. And that's why we have this thing.
So what is this surface?
This surface is orthogonal to this trajectory. If I shoot particles, they are hyperbolas. They are hyperbolas, and I take a surface orthogonal to all these hyperbola. And let's say that goes to negative infinity. This is asymptotic like this surface given by this. They are not plane orthogonal to all these surface, but this surface. And that's going to be the surface that the waves will have the same face. And that's why we have this thing or those things on the exponential.
Wait, and this is exact, or this is the asymptotic of the surface.
When we go to negative.
So it's the first one in the asymptotic.
That's not right. So we can see this classical. This explanation.
Sorry?
So this is classical. You can see this picture. This is solving the classical Newton equation. I don't know if I can talk more about attractive case. Depend on you, but that's basically about the repulsive case.
Yeah, so I mean, I guess we're just going to have Evo after.
Okay, sure.
3. How much longer?
If I can have 10 more minutes, I will explain to you the extra degeneration in the attractive case.
I mean, I think 10 more minutes we can definitely do. If it's going to take longer, then maybe we can do another time.
I hope not.
Right, I mean, then it's
okay.
You can do it and then we break a bit.
Okay, thank you. So for the attractive case, everything is same. When we go to the positive energy part, I have told you how do you find that, so I don't want to take more. We have everything. We go to the negative energy, which is the classical picture, where we have
sorry, before you do this, then what is the relevance of those fronts? The red curve that you.
Yeah, this is like the wavefront. So
yeah,
so this when we go to the quantum picture, the wave should have the same phase.
Yeah.
And that's why we have if you compare the picture, compare the function, the asymptotic behavior of the function, it will give you Or this is actually the correct one.
The argument is linear.
The argument here is sine r plus kr logarithm kr is the case.
So you fix z, and then you.
Yeah, this is not z is like r here. Z is like r. Well, the r I was using.
Z is like the r you were using.
Yeah, so
Because it's like the distance to the origin. Okay.
yeah. So I have that. That in the expression. But I did not go to the detail how to study, how to get that. But if you really study the scattering, useful scattering, this is exactly the thing appeared in the bracket.
But it's the behavior at minus infinity.
Yeah.
Not at plus infinity.
The plus infinity will be similar but not the same. Not as same as this. It will be same. Similar but not same. It will also have logarithms.
No, I think this is because you're looking at the picture in the other direction. There's the set of beams that are going to end up in one direction.
Yeah.
No matter where they originate.
Yeah.
Because otherwise the parabolas are going to go in all directions.
You mean the hyperbola?
The hyperbolas, yes.
Oh, yeah.
You only have a simple behavior as t goes to minus infinity,
Oh, I see,
or
yeah.
as t goes to plus infinity.
I think we will, if we're going to study this direction, we'll study the different theta angles,
Yeah, exactly.
the scattering angles, and in
And then
fixed theta, it will have some behavior. That's the distribution of the Russell. Okay, let's go to the negative energy for the attractive case. And as usual, as a usual convention, I will set n to be this, which we call principal common number. Formally, just put it arbitrarily. If you want to use the result before, so we just do this substitution to the solution before. Okay, it will give you a solution in the negative energy case.
So,
Yeah, we just do this substitution formally, where k is imaginary. We just do this formally to the formula before. We will have a solution in this case. And if you are looking for L2 solution, they will be given by the formula. Okay, and n must be integer. If you allow, sorry, then non-negative must be integer. So I don't need to argue, and 0 is a natural number or not. That's the solution if you want L2 solution. Oh, I should write this.
So L, 2L plus 1, N plus L.
Yeah. L is the Laplace function, Laplace polynomial. So yes, there are polynomials multiplied by some e to the power, which have decay, strong enough decay in the infinity, so that it's 2.
So these are the bound states, right?
Yes. Okay, and n must be smaller or equal to n. N minus 1, I think. Yeah. Yes. So the beautiful things happen, or the magical things happen that when, for example, n equals 0, we have n equals 0, and n equals 0. When n equals 1, we have n equals 0, and n equals 0, and equals 1, and equals 0, and so on. So on each n, we will have n squared states. So this is the extra degeneration we mentioned at the beginning, because usually we only have 2l plus 1, but this actually is 2l plus 1 squared. If you set 2l plus 1 equals n. And this is why we have the picture of the, that error. So this is n equals 1, so 0. Because we have two spins, so we have two states here. When n equals 1, so you have 2 times this word states, so allow you have this line, and then you go to the next line. It's a periodic table. That's exactly why.
So N is
L is the
like
y element.
N.
N is this.
And so you say that what each values of N,
There will be n squared states.
there will be N squares.
And possible.
Go ahead.
And if N is 0,
Thank you. And that's why we have it. So because the electrons cannot have the same state because they are thin, so they cannot have the same state. So they must be with different numbers along with 2 spin. So that's exactly why we have this table, because okay, when n equals 1, there are only 2 states allowed. When n equals 1, there are 4 times 2 spin, so 8 totally. That's why we have these lines. So we have the parallel table.
Shouldn't there be some sort of e to the minus r squared or something like that?
It's inside here.
It's inside.
Yeah, it's polynomial times that's
If people look here, function or something like that.
exactly like a function. They are polynomials with a z measure. L2 of them. Okay, then I just go to this explanation. Can I read this solution? So classically recall that in the Coulomb potential is vector. Which is called the Lagrange length, I think. Discovered many times.
Runge lens.
Yeah. I think Lagrange, the first one was on there, but
Lagrange.
yeah, but no one remembered, I guess. At least Lagrange never, but lens is part of complicated. So this is conservative in the classical case. So quantum way would just be this operator. These two are exchange, the lead bracket will be 0. And moreover, if we are in this stage, and we define this operator on this state divided by this eigenvalue.
Just a question.
Yes.
So P cross L, so you have a product, and so you have 2 ways to make it into, or like if you go to non-commutative, then it's here. But then, oh no, and I guess if it was plus L plus P.
Yeah. So again, in non-knowledge,
this the one correct.
yes. So in non-knowledge, they said it's easier to calculate. It's commutative. I spent like a day and one night to calculate that, but it's correct this way. It's actually a very hard example. But I calculate that at least once in my life. It's correct. Fortunately. If we do this, then we do some easier calculation.
Which is
Yes.
U.
Yeah,
So
U is
it's
A
just-
divided by this eigenvalue. If we are in that state, because we want to study how many states could be in energy. Then, because they are vectors, three components, we'll have these results. So if we calculate the commutator, and finally the classical one. Okay,
You don't want to call it LJ. I think you have two eyes.
one for negative bonus. Sorry. This is easier to calculate, but if you calculate that, and if you are familiar with the thing happens in the sport space, this is the argument. So we have extra symmetry in this case. And what's that? This framework product of three rotations. And classically, we know that this angular momentum will give you a representation of this three algebra. That's why we have the 2L plus 1 state, because if those three is just S2C and S2C is started very well. So you will expect that 2L plus 1 here. But we have this one. So, and how to find the representation of the 2D algebra? The product, sorry, the direct sum, just do tensor product. So we will accept another thing. So that's something we expected, because we must have two copies of things tensor together, and tensor together, so dimension is. So this is not surprising. Of course, I need to tell you that, for example, I need to tell you that if you go this, in this case, so they have some F. But basically, that's explanation or geometric explanation why we have extra degeneration.
Do you have extra what?
Degeneration, because usually in the rotational invariant potential, we only have this degeneration. So this dimension of eigenfunction have the same eigenvalue. Given L, we have this, but in this case we have this.
So you have more, basically more conserved quantities than you thought you would have.
Yeah, more conservative quantity or more symmetry.
Okay, so because in addition to L being conserved, right, or
Yeah.
commuting with the Hamiltonian,
Right.
you also have U
Yes.
commuting with the
Yeah.
Hamiltonian. But these are like different,
Yeah, they are
linearly
independent.
independent. So
Yeah, and they have this relationship which gives you the 4-dimensional rotation. So we are like on the 4D rotation. So we have the 4D angular momentum. This is very potential for respect of 1 and they're asking. In these two cases, we have extra dimension.
is there some explanation for why you have 4-dimensional? Other than like
In these two potential, I guess people just calculate on that. Yeah, but this is of course, this is known, as I told you, by Lagrange. You have this extra conservative law in the classical case.
But in the classical case, or maybe here, like, could you have had more? So in the classical case, and this gives you a super integrable system. You have 5 conserved quantity in 6 dimensions.
Like that.
I know there is nothing more you can do.
I think so.
So like, can you say that whatever potential you take, you will never have a bigger degeneracy than this one?
I don't think I can say that, but I can only tell you there's no other reason why we have this. For example, in the other potential, this is the usual potential. This degeneration, I can tell you without any knowledge of the potential, as long as rotational invariant. But this I cannot until it's smaller.
Yeah, but suppose you had another potential and
Yeah.
you add another operator A, it need not be exactly this type.
I think it really depends on this. Yeah, because if you want, this is a representation of the Lie algebra, and that theory tell you how many dimensions you should expect.
Yeah, but is this the algebra as big as you can get?
Sure.
From some kind of theoretical reason, if
Yeah.
you have in 3D.
Yeah. I mean, SO3 you expect this, and the SO4 you expect that. There's this two algebra. Yeah, because this is just SL2C, so SL2C is something last time.
All right. Well, thanks. So, bit of material. Great. Maybe we stop for 10 minutes and then everybody, are you going to use the board or?